Okay, so today I will talk of fppf and Étale Sheaves, and all of this is work in progress, and I'll try to explain what is proven, what is not, and what is almost proven. But so first, I guess the starting remark is that the Zariski topos has some well-known topoi, and so here I will be interested about the subtopos of Étale Sheaves and the subtopos of fppf Sheaves. And so the first remark is that subtopoi correspond to what is called Lex modalities. Theory. And so first I will give a short introduction to Lex modality. So I will not give the full definition of what is a Lex modality. What I will do is I will give a useful way to build some Lex modality. And for this, I need the definition. So let L be a family of proposition. So you have some type and a family of proposition indexed by that type. Then we say that the type is L local if for I in I and for map Li to X, so recall that this is a proposition. We ask that there exists a unique lifting of this diagram. So what it means intuitively is that if we can build an element assuming the proposition, we can actually build an element in the type. So the map from 1 to X is just a point in X. Which, assuming the proposition, is equal to the one we started with. And so overall, it means that when trying to build something in X, we can assume Li for any I. Yes, so then. So first proposition is that local types are closed under sigma and identity types. So this means that if we have a local type and a family of local type over it, the sigma type is local. This means that for all x and y in a local type, x equals y is local as well. It's also closed under dependent product over any type. So here we can use any x. It doesn't have to be local, but we need to do a product with this one and local. And so the final one is that so let's say UL is the type of type that are local. And UL is local. So this means that we have sigma, identity type, phi type, and a universe for local types. And so a consequence of this that says the remark is that local types common therefore. If you have proven something in homotopy type theory, you can interpret it in the local types. You have to beware to replace any arbitrary type by a local one, but things work out. So, okay, so I don't want to go into too much detail of this.
What's it saying? What you have to do to the natural numbers, entity types, sums, so on, inductive types, you have to localize them.
Yeah. Yes. So one thing I didn't mention is that given such a family of proposition, you have a way to localize any type. So for any type X, there exists a type that I will denote. We say M of X, that is L local. We have a map from X to M of X, and that is universal with respect to a local type. So this means that for all Y and local and map from X to Y, there exists a unique in filling this diagram. And so if you want to consider another constructor than this one, so for example, natural number, what you need to do is to apply a localization to the type you're interested in.
Okay, and the localization of a sum type where the index type is not local, it's just the sum type over the localized index.
I don't think so.
No, not necessarily, so it's more complicated.
I'm not sure it even makes sense, because if you have a map from A to U, it does not give you a map from the localized of A to U.
No, but to the U L. If UL is a local.
Yeah. Is this so? In this case, you can define something, but is it equivalent? I think so.
So what I actually wonder is, so if you have a proposition, or say maybe construction, how does it transport into the L local types?
I mean, if you have already a type family which is defined on the localized thing of your index, then you can do something.
Yeah, that is yeah.
Mm-hmm.
But otherwise, it's not clear what it is.
Yeah.
Okay.
Yeah. Okay. So. Okay. So now, let's go to the fppf Sheaves definition. Say that the type is an fppf sheaf if it is local with respect to the positional truncation of a root of a polynomial for G monic non-constant. So here indeed we consider a family of proposition indexed by monic non-constant polynomial. And yes, so that's how we define an fppf sheaf. So what it means is that when you try to build something in an fppf sheaf, you can actually assume that any monic non-constant polynomial has a root, so that the ring is algebraically closed, one could say. And it's correct to do this to build an element in an fppf sheaf. Yeah, and so the first remark is that the fact that this corresponds to actual fppf sheaf is a conjecture. So let's say it's a warning. Does not correspond. Correct external motion. Okay. So another remark is that in fppf the FP stands for fidèlement plat, which means faithfully flat. And so a definition that would be in some sense more natural is to ask to be local with respect to the truncation of the spectrum of any faithfully flat algebra. And so it is conjecture that both are the same. So it is conjecture that being an fppf sheaf is developed in positional truncation of state A local for all faithfully flat. We need to present so that's what justify the name fppf. And if this turns out not to be true, that both are equivalent, then presumably the correct notion of fppf sheaf would be the one using any faithfully flat algebra. But for now, I've given this one because we made more work on this one than the general one, where it's a bit complicated to prove much because we don't know that much about faithfully flat algebra, basically, synthetically. Okay, and so another remark that is more concerned with having some analogy with condensate is that so in condensate at some point you ask that if not spec K, you have the truncation of spec K. So I will explain later on how this relates in more details. But the remark is that let's conjecture. So if A is flat, then A is faithfully flat, even with not. So here again, there is the idea of localizing the truncation of something that is not empty. But I will get back to this so that it makes more sense. Okay. And so now, okay, so I will cheat a bit because when trying to define Étale sheaves, you do something very similar. So I'm just going to erase the relevant part so I can have Étale sheaves.
You have to replace the number as well.
Yes, indeed. So a type is an Étale sheaf if it is local like this for any polynomial monic, non-constant, and unramified. Unramifiable, sorry. And so, what does it mean for G to be unramifiable? Actually, it's equivalent to not, there is an R in R that is a simple root of G. So G of R is equal to 0, and G prime of R is different of 0. So it means the set of simple root of G is non-empty. And actually, you can reformulate this as an open condition of the coefficient of G, but I won't do it because it's a bit complicated to write down. But this is an open condition of the coefficient of G that just asks that something is different of 0. Okay, so here I can replace it here by Étale. So being an Étale sheaf is the same as being Speke local for all. And here I will use faithfully flat finitely presented Étale algebra. So I will not define Étale here for algebra, but I think it will be defined in a later talk. But for my talk, it's not very important.
You use twice Étale, different meaning.
So yes, something being an Étale sheaf is defined from Étale algebra. That is confusing terminology. So one thing we did in the notes is that we try to use formally Étale for this one and Étale sheaf for the other one, but you should not confuse the two. So yeah, so Étale sheaf are defined from formally Étale things, but they are not the same at all.
Yeah. So this Étale corresponds to Étale scheme, and Étale schemes are not the same as Étale sheaves, which are schemes.
Yes. Yes, and so a remark is that while for the fppf one it was conjectured to correspond to the external thing, but in a maybe optimistic fashion, here we have much more reason to believe that it corresponds to the right one. And so, yeah, so because it is proven in the paper by Gavin Wraith that so that the theory of local ring where unramifiable polynomials have roots, you can consider this algebraic theory, and its classifying topos is the Étale topos, so the topos of Étale sheaf in the usual sense, which it's not sufficient to immediately deduce that this definition works well, but it's a very good sign. So, okay, so for this one, we are much more confident that it gives the correct thing. Yeah, and so now I will give some results. Yeah, so one remark is that it's very clear that if I mean, being an fppf sheaf is more restrictive than being an Étale sheaf because we just added a condition here. So yeah. Yeah, and so what I want to present here is that schemes are fppf sheaves. Okay, and so here I have the lemma that has been quite fun from a traditional perspective. So let's be the proposition, let's say, such that, so we ask that R is P local for U, an open proposition, U is P local, and the type of U in props that U is open, so the type of open proposition is P local. Then any scheme is P local. So yes, so you just, in some sense, you just need to think to check. So yeah, in some sense, you just, if you want to check that all schemes are local for some type, you just need to check that the base ring is P local, that open proposition are P local, and that type of open proposition is P local. And from this, you conclude that any scheme that is anything that is covered by open that has an open cover by affine is P local as well. And so okay, let me do this. So let's say first step, any affine scheme is P local. Here we just have to recall the definition of state A. So it's a morphism of algebra from A to R. And the product over any type with value in P local type is P local. So for example, we know that A, R, this is P local because R is P local. And then you have to check a bunch of conditions to guarantee that it is a morphism of algebra. But actually, if you write down the type precisely, you just have to use closure by any product, sigma type and identity type, to conclude that this is P local. And so any affine scheme is P local. So that's already quite nice. So now let X be a scheme. So we assume a map from P to X. Let UI be an open affine over X. Okay, so then for any I, we have a map from P to X, and then so this is not this gives us an open in P, but actually we assume that any open proposition is P local. So we know that there exists things like this. So to begin with, I will just show that there merely exists a lift, and later we will check that it is unique. So at the moment, I am trying to check a proposition. And so, okay, so here I use UI. Let's call this one VI. Let's call the map F. And so what it means for the diagram to commute, it means that for small p in P, you have that P belong to F-1 of UI, if and only if the open proposition VI all. Okay. So now we will use the fact that UI is a cover. So what it means that for all P in P, we have that P belong to F minus 1 of Q1 or P belong to F minus 1 of UN, let's say. And so actually this is equivalent to P implies V1 or Vn. So this is an open proposition, so we know that it's local. So we merely have the lift here. Actually, there is a unique one. So it means that the proposition V1 or Vn holds. So now, let's say Vi holds. So what does it mean? It means that for all P, we have that P belongs to F minus 1 of UI. And so actually it means that the map from P to X, so the map F from P to X factors through UI. And so since this one is affine, and we have seen that affine scheme RP local, we now have a lift here, and that's indeed the lift of we started with. Okay. And so now we need to check the lift is unique. So to do this, we assume two lifts X and Y. So the fact that both are lift of this, actually what it means is that P implies X equals Y. And from this, we need to conclude X equals Y to conclude that the lifts are the same. And actually we can do this because so X equals Y is a proposition. So it's enough to prove the mere existence of a lift here. And we can do this because X equals Y is a scheme. And we just proven that when we have a scheme here, they merely exist. Okay, so now that we have this, we want, of course, to use this to show that it's fppf sheaf. Okay. And so now the idea is to just use this. So we have to check that R is an fppf sheaf, but for all open, the open is an fppf sheaf, and this type is an fppf sheaf. So I won't do all the part. I will. I mean, I can do the part with U open. It's pretty fast. So let U be an open proposition, such that we have G monic non-constant such that G having a root implies the open proposition U. So here, the fact that there is at most one lift is clear because this is a proposition. So what we need to do is to find such a lift. And so here, the key ingredient here is that we have not spec Rx G. So this is because when we try to prove a not, we can use excluded middle, and so we can reason on case, we can make a case distinction and find roots. So I won't go into details here. But so we have that this implies U. So from this we conclude not U, but open proposition are not stable. So we have to. Okay, so now let me go. R is an fppf sheaf. Okay, so let G be monic non-constant. Okay, so we want to show that given here to R, there is a unique lift. So here what I will prove is that this type here is equivalent to R, which is not exactly what I need. What we need is a tiny bit more, but I feel it contains the important idea already. And so how do I foresee? So we have the co-equalizer in sets. So the co-equalizer is and here I need to add two copies the spectrum. Okay, I will not have enough room. Say let me write AG for this algebra. And then have it. I have two projections going to the spectrum of a G, and this is actually a co-equalizer in sets. So this is not a co-equalizer in types, but in sets it's work. And so now I can exponentiate this with R, since R is a set, and I get an equalizer like this. And so here, when I exponentiate, I can use duality. This is just AG. Then here, when I exponentiate with R here, I get two maps from AG to AG times AG. So one of the map send X tensor 1, and the other send Y to 1 tensor Y. And so I know this is an equalizer diagram, so I just need to compute the equalizer of this. But here I have a map of R modules, so I can just compute the kernel. Yeah, see where psi of X is equal to X times Y minus this. And so, so I know that map from the proposition integration to R of the kernel of this, and so I need to understand this. But here the remark is that AG is actually as an R module. So it's not a definition, it's an equality as R module. It's the module that is, so say G is equal to Xn plus Xn minus 1 plus some smaller degree term. Then it's actually generated by Xn minus 1 to 1 as an R module. So here, if I look at this using spaces, a map. So here it's the free module generated by xy, so xj with one small, actually small n minus 1. Yeah. Zero, yes, sorry. Here I need a 0. And yeah, and so if I look at what this map is like, well, I see that it's then xi to xi times x0 minus x0 times xi, and so the kernel is just the thing generated by 1 by x0. Since this is the basis, just need for kernel equal. Okay. Okay. And so from this, I know that map from this to R, this is actually equivalent to R. And what I need precisely is to show that the canonical map from R to this is an equivalence, but you can check this from the definition, but I will not do this. Okay. And so, yeah, and so now I want to go a bit more informal, I guess. So, and so the one question that is quite natural to ask is, well, we have these fppf sheaves. We know that they form a model of homotopy type theory. And so rather than defining fppf sheaves inside synthetic algebraic geometry and working with them, maybe we could work directly inside fppf sheaf, so interpret homotopy type theory directly there. And so presumably what we would get is something somewhat similar to synthetic algebraic geometry, but not exactly the same. And so here I want to present, let's say, what I expect this to look like. So the proof have not been done in details. So, okay. Okay, so okay, so five, let's say, 14 internally. And so here we start from the pre-shape model. So we start from R of the ring that is not necessarily local. Duality or finitely presented algebra. And choice scheme, so full choice, not the size key local one. So okay, in this context, we give a definition. So topology T is a family of finite sums of affine schemes. Such that, so we need that one belongs to T. T is stable. And so here the idea is to model to imitate the Grothendieck topology. So usually a Grothendieck topology is defined using cover, not proposition, but it's also defined as being stable by pullback. So here we just define the fiber of the cover. So maybe a definition f from x to y is a T cover if the fibers of f are in T. So the fact that it's defined fiber-wise means that cover are stable by pullback. We use finite sum because cover are a finite family of maps. And so stability by sigma is stability of cover by composition, and top correspond to the trivial cover being part of the topology. So, okay. No.
Okay, so the goal is to define the corresponding leg modalities.
Yes.
Okay.
To define sheaves corresponding to the topology. Yeah. Yeah, and actually we can do this relatively easily. Definition, X is a T sheaf if it is X local for X belonging to the topology. So that's a Lex modality that we can use. So now I need the definition. T is subcanonical if R is a T sheaf. And so now we have a conjecture, let's say. So the model T sheaves satisfies. So for T, that is subcanonical. So duality for R. Say duality for finitely presented algebra. So here to have this, we had duality for finitely present order algebra to begin with. And then if the topology is subcanonical, we can see that the statement of duality is actually itself a sheaf. So it is just preserved. And for x in T, we have that x is merely inhabited. So this one is new. It's basically what we are trying to force to be true by considering the model. You know, by considering the sheaf, we consider the types that thinks that x is merely inhabited. And so in the model of those types, we actually have this. And then we have a T local choice. So what is T local choice is, let's say you have a map in space A, some surjective map here, then there merely exists a T cover. So a map whose fiber are in the topology, a T cover like this, such that you have a section like this. So this kind of looks like Zariski local choice, and so how to see that this corresponds quite precisely to Zariski local choice. For this, we need to define some topology. The Zariski topology consists of the finite sum like this when f1 fn integrates 1. So okay, so here you have to check that it is a topology, which is not completely obvious, but not too hard. You also, so for this to work, you have to check that it is subcanonical. Here you have to do some algebra or localization. That is actually not so easy, but doable and very well known. And so, okay, so if you start from this topology and you apply this conjecture, you get a model where you have duality for finitely presentable algebra. You have for x in the topology this, but if you look here at the topology, this precisely means that R is local. And here you get T local choice. So for all map like this, you get a cover by maps whose fiber are this form. And so showing that those are Zariski cover, I didn't do it, but I expect it to be true. So because fiber-wise, it's a sum of open proposition. So in the end, it's a finite cover by open proposition. That sounds very reasonable. And so actually this gives us a model of synthetic algebraic geometry. And so in the foundation notes, you have this case written in more detail, something very similar to this. Okay, and so now the question is, let's go with order topology. So the fppf topology consists of the finite sum spec A1, spec AN such that A1 AN is spacefully flat. And Étale topology, you do the same thing, so that A1 times AN is Étale. And just in fact. So yeah, so there's a question of knowing if this topology. So the first remark, which I should start with, is that we have an inclusion of topology. So Zaleski in Étale into the fppf. So here, this part, this means that this algebra is basically flat. When one, so that's what this inclusion means. This I not check, but it sounds very reasonable. This one is obvious the way I define. Yeah, and Étale. Yeah, indeed. So yes, so this should be checked, but I expect this to be true. This inclusion here, I set up things in a way where it is obvious, because here I ask for Étale and face fully flat, and it's about just face fully flat. And so yes, so fppf is subcanonical. So here I actually this idea of using the finite sum such as the product as something I thought about this last evening, so I haven't checked it yet. But what I checked is that R is spec A local for all A things fully flat. So since the finite sum of the spectrum is almost the spectrum of the product, the problem is that in the pre-shift model you don't have zero different of one, but so probably that this implies that the fppf topology is subcanonical is where I'm going. And so how much time do I have left? Not much. But so the question is, what happened when we apply this conjecture to this various topology? And so we get of new formal system. So we start with the pre-shift. So the first question is, what do we have on R? And the second is the white choice for affines. So in the pre-shift model, you have nothing on R. And what choice you have for affine? You have full choice. Okay, you can go to the Zaleski topos. Here you have R local. And you get Zaleski local choice. So with Étale, what do you have? So you get that this is merely inhabited for a face fully flat Étale. And here you get something like Étale local choice. So for any subjective map like this, you get a surjective. So here this map is always subjective, by the way. So you get a surjective Étale map such as you have this. As you have this. So this in particular, it means, for example, that unramifiable polynomial have roots. Yeah. And it also means that the ring is local because we have the inclusion. So fppf. So I will state for a phase-free class. And so here, for example, one can show that this algebra for geomonic inconstant is phase-free class. So it means at least that the ring is algebraically closed, that it is local because we have the inclusion, and possibly more. And so here you get something that we might call the flat local choice. So you don't get here, you don't get a Zariski cover, you get just a flat map. And so yeah, and so I think one remark that I find interesting is that what if we try to do this for countably presented Boolean algebra? So we start from a breadsheaf with a generic Boolean algebra and duality for countably presented and full choice. And here, when we try to localize the Boolean algebra, C as a ring, you actually have that the local Boolean algebra actually implies that B is equal to 2. So why? So if it's local, you know that 0 is different of 1, and you know that for all x is invertible or 1 minus x is invertible. But being invertible in a Boolean algebra, it means being equal to 1. So you get that x is equal to 1 or 1 minus x is equal to 1. So, so you get the Boolean algebra. Here you get something which is like Zariski local choice for Boolean algebra, which I think actually implies full choice. I don't want to get into too much detail. And then there is the question, well, what if we try to go for the... So Étale, I don't know how to make sense of Étale for Boolean algebra. I'm not sure it's relevant. But here one can look at what is a face-fully flat Boolean algebra. And B face-fully flat, B a Boolean algebra is face-fully flat. We can leave to inject in B. So what you do here when you use face-fully flat Boolean algebra is actually forcing the completeness axiom. So if not spectrum of B, then it is merely inhabited, and you get the choice corresponding. And so here there is some a lot of details to be checked, but that's the picture I wanted to give. And so thank you for your attention. Questions? Yes.
Can you expand on this fully flat implies that you inject screw into B?
Yes. So I think first you need a lemma, like any two module. So you see 2 as a ring, so as a Boolean algebra. Any 2 module is flat. So flat means that answering with any 2 module preserve exactness. And so now you want to prove. So you know that a face-fully flat map of algebra is injective. This you can prove in general. And what is not general is the converse. So assume that 2 in B. We want to show that B is face-fully flat. So first we know that it is flat because any 2 module is flat. Yes, and so to check that it is face-fully flat, actually it's enough to know that for M two modules and tensor 2b equals 0 implies m equals 0. So this is also well known. By the way, this lemma I didn't check that constructively works, but it sounds very reasonable.
More generally, over the field.
Okay. Because
So
I
if
guess
it's a finite field.
sorry.
I mean, yeah, I mean, it's more general. So it's about field.
Over any field. Yeah, it makes sense.
It's in the West.
The idea is that finitely presented module over a field are free, so they are flat. And then you know that a colimit of flat is flat, a directed colimit, so you conclude this way. Okay, so this is good. Yeah, but so you just need to prove this to have faithful flatness. And actually what you do is that you have an injection of 2 in B by hypothesis. You know that M is flat because any two module is flat. And so you know that you have an injection like this, and so you have this property. Yes.
Okay, so just one comment and a question. So, I mean, how can we use this in synthetic algebraic geometry? I mean, one thing is, I mean, we know that the Zariski topology is quite false, so sometimes it makes sense to calculate more.
Yeah, I mean, this one we know it's useful.
Yeah, but Étale, so for example, Étale may be useful to do some other topology calculations, as we know. And so what about fppf? Well, when we have well, we know that schemes are fppf sheaves, and so now we have a moduli problem that would like to one would like to know whether our modular problem is represented by a scheme. We know that our functor has to be an fppf sheaf. And if it's not, well, then,
not a scheme.
No, well, the way out is just to take the fppf sheafification and hope that's then represented. So just, I mean, as an application. I mean, this is what one does classically, for example, for the car scheme, when you consider line bundles, which are not fppf local, but you just make the problem fppf local, and then you can have the hope of finding it representing.
Okay, I see.
So it's, I mean, so in this case, I mean, because I mean, as the more you go to the subcanonical topology, the more representable something can become. So it's and so this was just a comment why I think that's really that's interesting for applications as well. Even if we are just interested in the sort of risky picture, but sometimes we have to go with topologies. And then question: can you rephrase your T local choice for when you start with the next modality? How would it?
I don't know how to do this. I'm not sure it makes sense. So you know, the idea of a topology is forcing some stuff to be surjective.
Yeah.
And then you have a choice in the sense that you have something that you have forced surjective. You know, you have just choice up to something you have forced to be surjective. But if I just have the proposition, I cannot really know what it is a propositional truncation, so I don't know how to formulate this. If that makes sense.
Another comment I'm saying, this conjecture, the first two parts seem fine, but it's, I mean, your hypothesis is that T is subcanonical, so that R is T sheaf, but that only depends on the truncation of T, or the family of propositions. But the T local choice is is more general. I mean, you don't know anything about the family T in general, except that it's what I mean. I'm a bit skeptical about that you get this with just this assumption that T is subcanonical. There might be something else.
Quite possibly, yes.
May I have another? So it would be very natural to put in these neighbors between Zariski and Étale. Have you worked that out?
I don't know. I don't know. I would love to know, but I don't know.
So for Étale, we know classically that the points of the Étale topology are the strict local rings, or the strictly Hegelian local rings. And I think I can see that you have that should be okay. But classically, I think there's some problem with what is the points of the fppf topology. There was a preprint by Stefan Breuer, and it's quite complicated with also limit ordinals, and
I think it's not a geometric theory.
yeah. So, but this is
I've
what
been
you
told.
get is looks geometric.
So maybe Nietzschevich cannot fit in this picture.
I think
I don't know.
For Hegelian, just
Yeah.
But also for the fppf, I think there's. I'm not sure. This maybe seems discouraging that it corresponds to the classical topology because they're describing the points. It's very complicated.
Okay.
I don't know. Maybe I'm misunderstanding.
Yeah, I mean, possibly this is optimistic.
But maybe it's not important.
Yeah, that's true. Maybe,
I mean, if you can make classical proofs using this, then
that's fine.
I mean, for the interpretation, the external one is only important that also that we don't want.
Yeah.
But the external interpretation of the Zariski.
Yeah, and that's the same. So for the modality for seeing monic polynomial to have roots, even if externally it doesn't correspond to anything people consider, it's still a useful modality to have around, and
yeah,
you can use it.
Maybe it's like AIC, absolutely integrally closed or something.
Yeah. So one remark also is, so when trying to work internally, so you can either try to work internally here or just use the modality in the Zariski topos. Here so working internally here, not much had been done. And I think one remark is that I don't expect the type of scheme to be an fppf sheet. Because from what I understand, you don't have fppf descent for scheme traditionally. And so this would mean that actually here working with scheme here is maybe not a good idea. And so maybe here one needs to consider stuff that have a flat cover by an affine scheme rather than scheme in the usual sense. And yeah, maybe doing this it works better. So yeah, thank you. So we have a break.